In a previous module, we talked about frame relay. We talked about the theory of frame relay operation. Remember, we were going to be sending data, specifically frames, over DLCs, data link connection identifiers. Those were our layer 2 addresses in the frame relay world. And now we want to go out and set it up using this topology on screen. We have a hub and spoke topology right now. HQ is the hub, BR1, BR2, they are the spokes. They're each connecting back into HQ via a PVC. And right now, I've already got IP addressing assigned to the serial interfaces on these routers, but they're running the default encapsulation type of HDLC. Let's go fix that. Let's enable frame relay on all of these routers, and we'll give some show commands and assess the situation, and if we have any issues, we'll build on that basic topology and see some of the other options available with frame relay. But we'll get started really simply, and I'm going to go into interface serial 1/0, and let's say encapsulation frame relay. And something else that we should generally set as a best practice, we should set the frame relay LMI type. LMI, that stands for Local Management Interface, and if we use some context-sensitive help, we'll see that there are 3 different LMI types. We can do a frame-relay LMI-type. Question mark. We've got these 3 types. We should match up with the LMI type of our service provider. And LMI, that is going to do the signaling between our frame relay router and the service provider's frame relay switch. I'm going to say in my case that the LMI type is ANSI. Let's do the same thing on the other 2 routers. Let's go to router BR1, and we'll go into interface serial 1/0 and say encapsulation frame relay, and the frame relay LMI type is going to be ANSI. Let's do it on BR2, interface serial 1/0, just abbreviate encap frame, and the frame relay LMI type is ANSI. We've now done a basic frame relay configuration on these routers. Let's give some show commands to see what the routers are currently aware of. We'll start at the hub router, router HQ. Let's do a show frame relay PVC for permanent virtual circuit. And I've got a couple of DLCs known to router HQ. I've got DLC 102, and that's going out to BR1, and I've got DLC 103, and that's going out to router BR2 at the other end of this PVC. Notice the PVC status is currently active. That means that I'm exchanging LMI information between my router, my DTE, and the service provider frame relay switch. Active also means that the frame relay switch is exchanging LMI information with the far side of this PVC. So I'm good between my router and the frame relay switch, and between the frame relay switch and the far end router. There are a couple of other statuses we might have. Inactive means that we're good between our router and the frame relay switch, but we're not good from the frame relay switch to the far end router. The other status we could have is deleted. Deleted means that we are not actively exchanging LMI information with our frame relay switch. So the problem is more localized than it is with inactive. Let's also do a show frame relay map to see what IP addresses I can get to over these DLCs. And I'm told that I can get to an IP address of 10.1.1.2, that's BR1, over DLC 102. Oh, that's correct, looking at our topology. I can get to 10.1.1.3 over DLC 103. Fantastic. In fact, let's ping those. Do I have reachability? Can I ping 10.1.1.2? I can. Can I ping 10.1.1.3? Yes, I can. I can get to these other routers. Now, by the way, how did this router know about this? How did I know the layer 3 address of that remote router? Well, I knew my local DLC, thanks to LMI, but how did I learn the IP address available at the far end of this PVC? We used something called inverse ARP. You remember how ARP works on an Ethernet network. On an Ethernet network, we send out an ARP message to say, here's a layer 3 address. Can somebody tell me the corresponding layer 2 address? Well, this is inverse ARP. We know the layer 2 address, which in this case is a DLC, and we're asking, can somebody tell me the layer 3 address? That's how we got these mappings. This is one way to get the mappings. Notice it's dynamic. Later on, we'll see that we can do it manually as well. We can create static maps, and there are times when it's good to do that. Also notice the broadcast keyword. By its nature, frame relay is a non-broadcast medium, but we want it to support broadcasts so that it can carry not just broadcast traffic, but multicast traffic, which we need for our routing protocols like EIGRP and Ospf. So it's a good thing that this dynamic mapping included the broadcast keyword. That's something that we can either include or not include if we're statically setting up a frame relay map. And at this point, so far so good, Router HQ, it can reach BR1, it can reach BR2. What if I go to BR1 though? Let's go to BR1 and do a show frame PVC. I only know about one PVC that goes back to HQ, and that's okay. I only have one PVC. I don't have a PVC going directly to BR2. However, how does this affect my mappings? If I do a show frame relay map, I only know about 10.1.1.1. That's something you need to understand about inverse ARP. Inverse ARP is only going to give us the IP address of the router at the far end of this PVC. It's not going to go, in our case, through HQ and then down to BR2. So we don't know how to get to BR2. Can I ping HQ? Let's try to ping 10.1.1.1. I can get to HQ, but can I get to BR2, 10.1.1.3? No, I cannot, because I have no mapping. And I suspect that we have a similar situation on router BR2. If I go to BR2 and do a show frame map, I only know how to get to HQ. I do not know how to get to BR1. I can ping HQ, I can do a ping to 10.1.1.1, but I cannot ping BR1. What can we do about this? Well, one option is we get another PVC. We get a PVC that will interconnect BR1 and BR2. That might cost extra money. The frame relay service provider might charge for that, but that's an option. Another option is to set up some static mappings. Let's take a look at both solutions. And to start off with, I'm going to create a PVC between BR1 and BR2. I'm going to set that up on the frame relay switch. I'm going to pause the video right now, get this full mesh topology set up where every router connects to every other router, and I'll rejoin you in just a few moments and we'll see what kind of connectivity we have then. As you can see from the topology on screen, I've now got a full mesh topology. We've got a PVC between each pair of routers, meaning that on BR1, if I do a show frame relay PVC, I should see a couple of PVCs. 201 going up to HQ and 203 going over to BR2. In fact, if I do a show frame map, I should now know how to get to BR2. Look at that. In addition to the mapping we had earlier, I've got a new mapping. I now know how to get to BR2. Let's try. Can I ping 10.1.1.3? I can. Let's go to BR2. On BR2, if I do a show frame relay PVC, I've got a couple of PVCs. Show frame relay map is going to show that I've got a couple of mappings. I can now ping 10.1.1.2. Excellent. And what we've done is solved our reachability issue by creating a full mesh of PVCs. However, that's not always going to be practical, especially in larger environments, because we could start to require lots of PVCs, and our service provider might be charging us for each PVC, and that could start to get really expensive. Remember the formula for calculating the number of links required to form a full mesh? It's n times n minus 1. And you take that product and you divide by 2. So for example, if I had 10 links, it would be 10 times 9, 90, divided by 2, which would be 45. 45 PVCs to fully mesh 10 different routers. That's a lot of PVCs. And in a case like that, we might need an alternate solution. And one alternate solution is to use frame relay maps. This is where, without paying our service provider for additional PVCs, we can statically create mappings on our routers to say, here's how we get to this IP address. We go out of this PVC. What I'm going to do now is pause the video once again. I'm going to get rid of the PVC between BR1 and BR2. We're going to go back from this fully meshed topology back to just a hub and spoke topology, and we're going to establish reachability not by using a full mesh topology, but by statically configuring maps. So hang on for just a moment while I pause the video and get rid of the PVC between BR1 and BR2. Our PVC between BR1 and BR2 has now been removed, and we're back to the way things were right after we set up frame relay. In other words, on HQ, if I do a show frame relay map, I know how to get to BR1 and BR2. But if I go to BR1 and do a show frame relay map, I do not know how to get to BR2. and that's because I only have one PVC, and I cannot learn via inverse ARP anything about BR2 because it's not at the other end of a PVC connected to this router. And I've got the same situation on BR2. If I do a show frame relay map, I only know how to get to HQ. If I do a show frame relay PVC, I only have one PVC and it's going up to HQ. And what we want to do now is configure full reachability using frame relay map statements. A frame relay map statement can map a remote IP address to a local DELC. And when we're setting this up, we probably want to include the broadcast keyword in our command. This is going to be needed to support not only broadcasts, but also multicasts that will be used by routing protocols such as Ospf and EIGRP. On BR2, let's set up a frame relay map statement. Let's go into interface serial 1/0, and we'll say frame-relay map. We specify the protocol. We're dealing with IP. Let's map the IP address of 10.1.1.2, which is the IP address of BR1. We cannot currently reach that. And to get there, we're going to go out of DELC, our local DELC of 301. That's going to get us up to HQ, and HQ is going to know how to get to 10.1.1.2 because it has a mapping. And we want to include the broadcast keyword here. That's something that we'll commonly do to support not just broadcast, but also multicast traffic. Let's go do the same thing on router BR1. Let's go into interface serial 1/0, and we'll say frame relay map IP. Let's give the IP address of BR2. It's 10.1.1.3. To get there, we're going to go out of our local DELC, local to BR1, our local DELC of 201, and we want to give the broadcast keyword. Now, do we have reachability? Let's check it out. If I do a show frame relay map, we see that I have dynamically learned how to get to 10.1.1.1, and I have statically configured how to get to 10.1.1.3. Can I reach 10.1.1.3? Can I reach BR2? Let's try. Ping 10.1.1.3. I can get to BR2. I can get to HQ. What about BR2? On BR2, if I do a show frame relay map, I know how to get to BR1. Let's try to ping it. Ping 10.1.1.2. I can still reach HQ by doing a 10.1.1.1. It might look at this point like we've solved our issue. After all, if I go to HQ, I still have reachability from HQ. I can still do a ping to 10.1.1.2 and to 10.1.1.3. Everybody can get to everyone else right now. But there is a major point that we need to understand. Whenever we set up a frame relay map statement for an IP address on a DELC, inverse ARP is going to be disabled for, in our case, IP for the DELC we specify in that frame relay map statement. This means that although everything seems to be working just fine now, if we were to reboot routers BR1 and BR2, they would not learn about HQ via inverse ARP because the frame relay map statement turned off inverse ARP for IP on that DELC. So they would not be able to get to HQ, and they would not be able to get to one another because they have to get to one another via HQ. So our situation just got worse. They went from only being able to reach HQ to not being able to reach anyone. To prevent this from happening, we need to replace the mappings on BR1 and BR2 that were learned via inverse ARP. We need to replace those mappings with static mappings. Let's go to BR1 and say, statically, here's how to get to HQ. Let's go into interface serial 1/0 and say frame-relay map IP 10.1.1.1, that's HQ. We're going to go out of our local DELC of 201. We want to include the broadcast keyword. And now if I do a show frame relay map, notice that both of my mappings are static. I still have reachability. I can still do a ping to 10.1.1.1. I can still do a ping to 10.1.1.3, but I'm not relying on inverse ARP. And I'm not going to take the time to do it here, but we would have to do the same thing on router BR2. But hold on, what about router HQ? We haven't given any frame relay map statements there. Is that okay? If I go to HQ and do a show frame relay map, these mappings were learned via inverse ARP. Is that okay? That's actually fine in this case. Because we do not have any static mappings on HQ, our inverse ARP process is not going to be disabled. And remember that a reason we wanted to use the frame relay map statements was to help with our scalability issue, to avoid purchasing additional PVCs from our service provider. And that certainly helped eliminate the need for extra PVCs. But we still have a scalability problem, don't we? Because we now have the potential for lots of frame relay map statements if we have a very large network. What can we do about that scalability issue? Well, something else that can help us out, and an approach that is commonly used in the real world for networks that are doing frame relay, is to use sub-interfaces. A sub-interface is a logical interface that is created under a physical interface. We've got a couple of types. There's point-to-point or multi-point, and sometimes you hear multi-point referred to as point-to-multi-point. And a point-to-point sub-interface uses just one DELC, but a multi-point sub-interface, it could use one or more DELCs. And with the point-to-point subinterface, it's sort of like a point-to-point leased line that we might have between a couple of routers. We have a router at each end of this PVC, and that's it. However, for each of these point-to-point PVCs, we're going to need to have a separate subnet. So we might have a subnet on the PVC between HQ and BR1, and a separate subnet on the PVC between HQ and BR2. And this point-to-point subinterface approach is generally most helpful when we have a topology like this, a hub and spoke topology. With a multi-point subinterface, we can save on address space because I could have, for example, HQ and BR1 and BR2 all belong to the same subnet as they do now. But in our case, with a hub and spoke topology, we don't get much of an advantage by using a multi-point subinterface. We will get an advantage by using point-to-point subinterfaces, but multi-point subinterfaces, they typically are most helpful when we have a full mesh or a partial mesh topology. But I do want to show you how to set both up. So what I'm going to do right now, in the interest of time, so you don't have to watch me type everything in, I'm going to pause the video again, and when I come back, I will have router HQ configured with a couple of point-to-point subinterfaces connecting out to BR1 and BR2, and we'll take a look at how that works, and then we'll take a look at a multi-point subinterface. But for now, I'm going to pause the video, create a point-to-point subinterface configuration, and we'll see you back in just a few seconds. What we have now is a point-to-point subinterface configuration on each of our routers. If we go to router HQ, let's just take a look at the syntax for how we set this up. We'll do a show run and take a look at serial 1/0, and we can see that the physical interface of serial 1/0 does not have an IP address. What we're doing is creating a couple of sub-interfaces. We say interface serial 1/0 dot, and then you give a number. You don't have to do it this way, but I kind of like adding on the DELC number as the sub-interface identifier. You could say serial 1/0.1 or .2, that would be fine, but I think it's easier to interpret the config if I just use the DELC number here. And this is a sub-interface for DELC 102, and I'm specifying that it's a point-to-point subinterface as opposed to a multi-point subinterface, and I'm assigning it an IP address. And I'm saying that your DELC is 102. I'm not having to dynamically learn this. I'm not relying on frame relay map statements. I'm not using inverse ARP. This is my preferred way of setting things up. And I've created another sub-interface for the DELC going down to router BR2, and you'll notice that this is on a different subnet. Different interfaces have IP addresses on different subnets. Well, that's what's going on here. Each of these point-to-point subinterfaces belong to a different subnet. This means that I had to go to router BR2, like you see in this topology on screen, and change its IP address to be part of this subnet. But if we take a look at my frame relay PVCs, let's do a show frame PVC. I see that my PVCs are active, and if I do a show frame map, I do have a couple of mappings showing up, but notice we're not seeing IP addresses. We're not seeing that 10.1.1.2 is at the other end of DELC 102, but that's okay. Since this is a point-to-point subinterface, if I'm sending traffic to the subnet to which serial 1/0.102 belongs, then we just assume it's at the other end of this PVC. We don't have to have a static mapping. We didn't have to learn that via inverse ARP, yet I still have reachability. I can do a ping to 10.1.1.2, that's BR1, and I can do a ping to 10.1.2.3, that's BR2. And if we go take a look at BR1, and we'll do a show run, we see that I've created a subinterface here as well, just one, because we just have one DELC, it's going back to HQ. And I've done something similar on BR2. On BR2, I actually had to update the IP address, put it on a different subnet. Now, do I have full connectivity at this point? Actually, yes, I do. I'll prove it. From BR2, I can ping 10.1.1.1, that's HQ, and I can ping 10.1.1.2, that's BR1. Here's a question, how do I know how to get to BR1? Basic routing. We could run a routing protocol, or what I've done, I just set up a default static route. Let me show you. If I do a show run pipe to include IP route, you can see the IP route command I typed in. Here's my default route, and it says, if you want to get to a network that's not known to your IP routing table, just go out of this PVC. So this is going to go up to HQ. HQ is going to know how to get to the 10.1.1.0/24 network, and HQ is going to forward it on to BR1. And I've given a similar statement on BR1. So this is a really cool approach, I think. We're not relying on inverse ARP. We're not having to purchase a bunch of extra PVCs. We're not having to create lots of frame relay map statements. We can just put our different PVCs in different point-to-point subinterfaces, each on different networks, and route between them. Now, there is another type of subinterface that we mentioned. It's a multi-point subinterface, and I want to show you the configuration of that. So once again, I'm going to pause the video, and we'll be back in just a moment to take a look at a multi-point subinterface configuration. I've now configured router HQ with a multi-point interface. Let's take a look at the config. Let's do a show run, and we'll check out serial 1/0. Here we have a multi-point subinterface. Notice the difference between multi-point and point-to-point. Still, I don't have an IP address on the physical interface, and I do have an IP address on the subinterface. However, now with a multi-point subinterface, I can have more than one DELC known to that one subinterface. So I've got one subinterface with two DELCs feeding out of it. And in this case, HQ, BR1, BR2, they all belong to the same subnet. So some might argue that we're conserving address space by doing it this way. However, it really doesn't gain us very much to do a multi-point subinterface in a hub and spoke topology like this. After all, if I go to router BR1, let's take a look at the config here. In order to get full reachability, I still needed to give frame relay map statements to get me to HQ and over to BR2. So my personal preference is to use point-to-point subinterfaces because it's not doing us much good because of this hub and spoke topology. A multi-point subinterface could help us if we had a partial mesh or a full mesh topology, however. And we also need to consider a couple of issues that we could have with routing protocols. For example, EIGRP. If we were advertising a network from BR1 to HQ and we were going into a subinterface on HQ, split horizon would be enabled. So that route advertisement would not go back out to the other branch router. We would need to give a command in subinterface configuration mode to say that we wanted to turn off split horizon for EIGRP. And what about OSPF? OSPF doesn't use the split horizon rule, but we could still have an issue. You see, we could have a mixture of frame relay interface types, like multi-point or point-to-point, or just configuring frame relay under the physical interface. This could cause OSPF to have different timers on different interfaces, preventing neighborships from forming. To fix this, we might need to statically configure the OSPF network type on each interface using the command IP OSPF network followed by the network type. I like to set the network type on all of the frame relay subinterfaces to point-to-point. That way, all of the timers match, and a point-to-point OSPF network type doesn't have a designated router, so I don't have to worry about a designated router election. Well, that is going to wrap up this somewhat lengthy look at frame relay. I wanted to start with just a basic frame relay configuration, turning on frame relay encapsulation and setting the LMI type on the interfaces. Then we saw that we had a reachability issue. We fixed that with a full mesh topology, and we said an alternate way to fix that without buying another PVC was to use frame relay map statements. And then we saw that we could use subinterfaces, and we contrasted both point-to-point and multi-point subinterfaces. And finally, we talked about a couple of issues we could have with routing protocols, like EIGRP and OSPF.